Hi, this is Group 3's DAAN AA1 project for the fall 2022 semester. My name is Vi Gata, and today my teammates and I will walk you through our project. And our project is COVID virality. So we'll be going over the abstract, how we created and executed our data models for this project, along with a code demonstration, as well as drawing a summary of this project, as you can see in the overview slide. So we move on to the next slide. Our project idea is based upon COVID. And as you know, COVID is the latest global health pandemic that caused the world to shut down during the spring of 2020. Since then, there have been several vaccines and boosters for the human race to help curb the spread of this viral disease. And since our project involved COVID and the virality rates, the CDC has many public data sets free for the public to use that our group used to answer the questions. So we move on to the next slide. The basic facts of COVID are that it overall has a great effect on older people, as well as all people with any respiratory symptoms such as asthma or pre-existing health conditions such as diabetes. So after looking over these COVID data sets as a preliminary data analysis, our group came up with 3 questions to help us complete our data analysis.
Thanks, Vi. I'll take it from here. I'll be going over the next 3 slides. So the first slide, I'm going to be discussing our research and business questions. The first question we came up with as a group, does the correlation between COVID-19 death rates vary by age group and geographical location? Location, we're referring to states in the United States. An age group, I believe we looked at 10 different age groups that was in the data. Second question is, who should be targeted to receive a 4th booster of the vaccine from resulting death rates due to specific contributing conditions? And our third question we looked at is obesity a condition that is stronger indicator of higher mortality for COVID than a respiratory condition? Next slide, please. Okay, so this slide, we discussed some of the observations we made from our initial exploration of the data. Firstly, the data being used for analysis was collected from the CDC and CHS and the US Census Bureau. The data being used is current as of 2022, so pretty recent. After doing our initial exploration of the data, it had already been cleaned up prior to by CDC, so we didn't have to do too extensive cleaning on that part. And the data provides mortality death rates for 23 different medical conditions, in addition to patients having contracted COVID-19. Our target variable we selected was COVID-19 mortality rates, and then the explanatory variables we used was state, condition, year, month, age, and group. Next slide, please. So this is another discussion on our data cleaning approach. As previously mentioned in the previous slide, the data was already kind of cleaned by the CDC, so we didn't have to get too extensive on that. The original data set had approximately 460,000 rows and 14 columns. After we did some of our final cleaning to align with our business goals, and removed some unnecessary columns and observations, we were left with approximately 310,009 columns. And that should be it. Next slide, please. And with that, I guess I'll pass it off to Nick for the next couple slides.
Thank you. Yeah, so just to continue a little bit more on the data cleaning. So as Brandon was mentioning, we had a very clean data set that came from the CDC in terms of there wasn't a lot of obvious mistakes. Really what this slide and the kind of the method and approach here is we had to reformat and kind of structure the data in a way that made sense for the questions that we were asking. And the first part of that was to remove some irrelevant data. A good example of that was the date as of number. One of the columns of our data set was the date as of, not something that's going to be super critical to what we were asking and what we were working towards. We also removed the District of Columbia and Puerto Rico, primarily because we were focusing on the 50 states. Not that the data wasn't clean or wasn't usable for those particular areas, but we were just, again, focused on the 50 states. Most of the columns of missing data were removed even before we got to it. The CDC had done a very good job of cleaning the data. One of the issues that we had to work with is, due to privacy reasons, whenever there was a death count of less than 10 per data set, they didn't give the exact number. And that's for patient privacy. So what we had to do was work out what we were going to do with those particular areas where the data was less than 10. In our data set, I believe the CDC kind of left it as just a kind of a blank number. We went with the option to just choose the number 10. You could have done 5, but again, all we knew from the data set is that the death count was between 0 and 10. We chose to replace that missing data with 10, and that's just, again, an assumption that we chose as a group and just something to consider when we're doing all these modelings. We also removed the aggregate values by year and by total, and we kept by month. Obviously, some of this is a little bit redundant, right? If you have the total by month, you can calculate the total by year if you want it. Same thing with the grand total. If you have each month, you can calculate the grand total as well. We chose to remove the by year and by total. And on the next slide, when we get there in a second, I will explain why we removed those. We did add 2 additional columns. This was to help normalize the target variable that we were looking at. When you just go by the sheer number of COVID deaths, you're going to be biased towards states with higher populations, right? New York and California have a lot of people live there. Obviously, they're going to have a higher number of COVID deaths. What we did was we divided the number of deaths by the total population to get a COVID-19 death rate. We felt that that was a better normalized variable to try to model towards because, again, you remove some of that inherent bias that you would get with states with a larger population. So we'll move to the next slide. And you can see on this graph, and this is as we're cleaning the data. So you can see there that 50% big red half semicircle there in the pie chart that's all ages, right? So that's the sum of everything else, which makes complete sense. That's exactly 50% of the rest. All ages is, again, not something that's going to really be usable in a model because, again, we have the age breakdown on the left side of that pie chart. And that's really what we're looking for with the all ages, or like I was mentioning before, all deaths, those categories. Just the way that the data was structured is not something we necessarily needed. And it was something that was removed before we did our modeling. On the right there, there's the word chart of all the different types of diseases that were kind of included within the data set. And again, that kind of goes back to some of our variables, but you can see that anything that's a little bit bigger, obviously, is something that is seen more. And some of the highlights there, you can see a respiratory, which makes sense considering that COVID-19 is known to be a respiratory illness. You can also see things like diseases, which makes sense given that all these particular things are conditions. Also, cardiac and heart were something that came up as something that was seen quite often. And then we'll move to the next stage, with next slide here, and we'll talk a little bit more about the factor analysis of mixed data, FAMD. This is essentially what our PCA was. We were looking at what are the contributions to variables. And the way that we looked at this is we kind of broke it into 2 different dimensions. Dimension 1 being a little bit of a higher contributor to dimension 2. And you can see that some of the things that make a difference, obviously COVID-19 deaths is on the top, in dimension 1 there. But as you get into the next levels down, you have things like states and state population, percent of population. Again, these are things that are important in terms of what factored into the model itself. So again, this is a FAMD, factor analysis of mixed data. That was our first step as our PCA analysis. I will now pass it over to Jacob to talk a little bit more about our modeling.
Thank you. Yeah, so our approach to modeling was that we wanted to use a combination of two models to answer our business questions. We chose to use logistic regression and random forest models. We chose this because logistic regression does a good job of predicting categorical variable types, which two of our business questions needed. And we wanted to use a random forest model because it's a little bit more robust and does a good job of combating bias and overfitting. So we wanted to use both models, so we didn't have to decide before running a model which approach we wanted to go with, and we could compare and contrast performance. Next slide. Yeah, so our first business question was, does the correlation between COVID-19 mortality rates vary by age group and geographic location? Before we modeled it, we looked at the box plots for each variable. As you can see on the box plot on the right for age groups, it does appear that there is a difference in means when you get in the age group 65 and above. I think that's very clear there. It's a little tougher to see in the state box plot just because it's so busy, but it does appear to have some variation from state to state. Next slide. So here are the feature importance results and the model results from the random forest model. Our logistic regression model was not able to find that age groups and locations together were a precursor for mortality rates. However, the random forest model thought both features were significant in predicting those mortality rates. A benefit of using the random forest model was that we were able to generate the feature importance from it. And you can see from the results that the random forest model utilizes the features age group, state, month, and year, and the model was high performing at predicting mortality rates with an R² of 0.78, which we all know means explains 78% of the variation in the mortality rates just from using these features. Looking at the feature importance, state actually ended up being the most important feature in this model with a feature importance of 0.34, and age group was still very important with a feature importance of 0.26. So looking at this, it's very clear that we are able to build a strong random forest model predicting mortality rates using age group and state, just with some time metrics as well. So we took that as an answer to our business question that the correlation between COVID death rates definitely does vary by age group and geographic location. Next slide. The second question we wanted to answer was which individual should be a target to receive a fourth booster of the vaccine from resulting death rates due to specific contributing conditions. So again, we wanted to look at the age groups, and we already went over that, but we can see on the right again that average death rates are higher for the age group 65 and above. And then on the left, we have the box plots for various conditions. And again, it's a little busy, but you can see there are conditions that do seem to have higher average mortality rates. And then next slide, and I'll pass it on to Jonathan.
Hey, thanks a lot, Jacob. So going into question 3 on slide 15, we analyzed our third business question, which was focused on determining if obesity or respiratory failure was a stronger predictor of mortality as a contributing condition with COVID-19. So we've all naturally heard from doctors and even individuals that when you have a respiratory condition and or obesity, that they were at higher risk, those individuals, for COVID-19. So we wanted to use the data that the CDC provided to prove that these factors are responsible for higher mortality rates. So from this data from the CDC, as you can see here from our logistic regression algorithm, from the first graph, the means are very different. The average being higher for respiratory illness than for obesity. It's pretty clear. There also appears to be many more outliers for respiratory failure, indicating that there were states that had higher mortality, much higher than that of obesity. The logistic model formula took COVID-19, it's there on the right-hand side, and compared it to the obesity and respiratory failures in the call. So the coefficients in the R export indicate that respiratory failure has a statistically significant code with a value of 0.00518, indicating that between the two, it is a better predictor for mortality. On to the next slide, on slide 16, here is the model for the random forest algorithm, which as well shows that the only condition more serious than respiratory failure when combined with COVID-19 was influenza or pneumonia. The random forest model categorized respiratory failure with a feature importance of 0.108, whereas obesity only attributed with a feature importance of 0.000895. You also notice that the R-squared value was 0.97, and the root mean squared error was very small as well at 0.00037. So this takes us into our conclusion, into our last slide. And our conclusions were not initially what we had anticipated when we started the project. As a reminder, looking at the 3 questions we looked at, does the correlation between COVID-19 death rates vary by age group and geographic location? Who should be targeted to receive a 4th booster or new specialized version of the vaccine from the resulting death rates due to specific contributing conditions? And is obesity a condition that is a stronger indicator of higher mortality for COVID than a respiratory condition? So from our logistic regression model, and Jacob touched on this a little bit, we were unable to prove from a statistically significant perspective that mortality rates varied by location. Our initial impression was that those areas where there were higher populations in more compact areas, such as New York or Florida, California, that these locations would prove to have higher mortality rates just due to proximity, just the amount of people that are as close as they are to each other. The random forest regressor model did show, though, that the mortality rates do vary by location to a statistically significant degree. Our second and third business question had some overlap, as the third business question, which was looking at which was the stronger indicator for mortality, obesity, or the respiratory conditions. The data indicated on both the logistic regression and the random forest model that respiratory conditions were a much higher predictor factor for COVID-19 mortality than obesity. So this enables us to use some of this data to assist in our second business question, which was asking who should be targeted for that 4th booster or the new specialized version of the vaccine. So it's clear that anyone that has a pre-existing or contributing respiratory condition should be looked at for a 4th booster, or at least prioritized for a 4th booster or specialized version of the vaccine before any other groups in order to mitigate potentials for death. Our data also showed, which is probably of no surprise to many of you, that age plays a factor as well. So we were able to see that age groups 65 and older as well show higher rates of mortality for COVID-19 contributing conditions, especially when combined with respiratory illnesses. And this concludes our presentation. We appreciate everyone's viewing and look forward to any comments. Thank you.